morning, folks. We're going to start up in a second. I can see there's a few folks online waiting for me to join in. I really appreciate folks who are waking up early in the morning here in week 7 to try out some data structures with me live. I know everyone else will watch this stuff when it hits Echo 360 later on, but it's good to be live. So, just going to start recording. And I'll say good morning again, everybody. Great to be back here in week 7 for more fun in COMP2300/6300 here at the ANU. Certainly, we've had some slightly warmer days recently, so it's not so annoying to be up early in the morning talking to you here live online. I'm really thankful for the faithful few who are joining me on our live stream this morning. I know that it's not all that fun to be on the live stream. I hope I'm actually visible to everybody. I'm just going to check some of my screens. Oh yeah, there's a picture of me doing the big slash motion. A few seconds behind as normal, but that's how streams work. I'm sorry to have this slightly strange lecture time, 9 a.m. Tuesday, and then another lecture at 9 a.m. Thursday. We've got 3 public holidays on Mondays this semester, which really messes up timetables. I'm thankful that we don't have to change any labs because of these public holidays. That is a real hassle if you have to change labs, but we only have to adjust the lecture times. We'll see if today's works. I might try a different strategy for next week. See if we can get some more people involved on the first lecture of week 8, which is a really important one coming up. Not to say that today's lecture isn't important, but they're all equally important lectures, but some are just more important than others. Before we start the content of today, I'll just briefly tell you what we're going to talk about this week. We'll be discussing this concept of data structures, which we've hinted at in many different ways over the last the 6 weeks of the course we've already had. I know people have been using things that are like data structures, working out how to use them for their assignment. But we're going to go through in some detail, carefully, and just say what I mean when I say an array, and I'll say what I mean when I say a record, and I'll give lots of worked examples, and all of the code will be there, and you'll understand how it all works if you haven't quite understood it already. And if you think you understand it already, maybe you'll learn something new or have a new inspiration of how to do it. This stuff is really important for your next assignment. So this is a lecture to make sure you watch whether you're up to date or not. So just a little bit of admin corner. We've got to get our coffees out for admin corner. Where are we at with this course? We're now halfway through the content, and we're not quite halfway through the assessment. I know that there's a big assessment this Friday. Your first big assessment item was the assignment 1, and we're really happy with the results we've been seeing. I was so excited to see the wonderful light shows that you folks created on the microbits. They were just awesome. I've seen many folks who put in inordinate amounts of effort, just way over the top, and I want to thank you for that. I particularly want to shout out to the person who had, I think, a 14,000 line assignment 1, which was probably a record. Completely valid way to write a program. Perhaps there would be ways to optimize that in future, I could say to that person, and to many people who had many thousand-line programs outlining their animation. Hopefully with things like data structures and the loops we've been going through and functions, which you now know about and have some more experience with, you can find ways to have high complexity in your programs without having a very long program itself, but still a very valid solution and evidence of a real engagement with how this course works, how the microbit works, and how we control hardware. There were folks who put in lots of effort and were doing things with the microbit that I didn't know could be done, and they are obviously really pushing the limits of what we're expecting in this course, which is amazing, and thank you to them. There are people who put in lots of effort just to get a handle of what we've been doing so far in the course, just to get a satisfactory basic light show working. And I want to thank those people too. I saw some assignments which were certainly maybe using more of the basic techniques we've gone through, but they had a lot of heart. The person who submitted them obviously had put a lot of effort into understanding these concepts and put a lot of care in assembling their assignment. And I was just so pleased to see them. The assignment results will be coming out later today. I'll be announcing on Piazza when they're available. We just have a few more things that need to be wrapped up so that I get every single assignment out the door in the one go, which is pretty cool. I will comment on one thing with assignment 1. There are a few people who could have put some more effort into the design document. Some things that come to mind are making sure that the Markdown formatting is really impeccable. It's very annoying for us to read a document in Markdown which doesn't look like Markdown, where all the line breaks are in random places. Like, we actually have to read this stuff, you know. So if your Markdown file is a mess, just consider how that works. Always try a preview of your Markdown file to make sure that the pictures are working if you've used pictures, or that the formatting you've used makes sense. Don't invent new formatting. Markdown has its own syntax. There's a page on how to write a design document well, which gives you some hints there. And make sure that one of the good things about Markdown is that it's supposed to look good as an HTML document, as well as the source code itself. So make sure the source code looks good, and make sure the HTML document looks good, and then you should be fine. There were also some folks who needed to write more in their design documents. The word limit was 600 words. There were some folks who wrote way too much, which was also a problem. That definitely is a word limit. But some people writing, 100 words or so, well, that's not quite enough. Even with the most basic programs, I think there are things to say about your work, to people who are really struggling just to get the basics together, which is a fine place to be, I'm happy to support you. Make sure you don't give up on the design document, because it's a place where you can show your knowledge in a different way and get some more marks that way. Second thing, mid-semester exam is this Friday. Stressful. I hope it's not too stressful, because one of my goals with this course is to prepare everyone really well for the assessments. You've had a quiz, you've had an assignment, you have a web page full of a huge number of previous practice exams, but I'm really focused on the quiz and the assignment. Those are the key preparations. The quiz and the assignment and the lectures and the labs. All of these things are the key preparations for your exam. So if you have a handle of all the labs so far, you have a handle of the content in the quiz, you've done well in your assignment, then you should be okay to take the exam. It's those things are preparing you for it. So of course I want people to revise and study and ask hard questions this week, but be assured if you've done all of the previous assessments and you've done all of the course content, then you're probably in a good place to do well in this exam. So you can go into it with those tools. One thing I will say about the mid-sem exam is that I'm going to release an important piece of information today, which will be a document that's the setup to a question in the exam. It's not going to be a trick question, like I'm showing you something that you can secretly work out some hint or something. It's just, there would be, sometimes in an exam question, there's some setup for a question, like context about it, and I want you to think about it. I want to give you the space to think about it this week, rather than have you panic and stress about it in the exam when you see it, because the information has to be like a page of info. It's not horrendously complicated, but it's just something I want everyone to have in front of them and be comfortable with, and read, have at least a day to just let your brain soak it in and think about the consequences of that. There's nothing tricky about this. I'm just trying to give you some more chance, reduce your stress, and improve your chances of giving me a response in the questions in the exam related to this that makes sense and is really good. Because basically what I want to do is make sure that everyone is really well prepared and gives me good exam responses. That's one of my goals as a teacher, right? So that's my way. You'll see that pop up on the Piazza and an email later today. Last thing, psych up for the second half of the course. It's been a big first half before the break, but the reality of this course is that there are some topics that are coming up which are pretty tough, and you need to be switched on to take care of them. I'm pretty much talking about the labs over the next 3 weeks, which are really going to test you. They require you to really be on top of the material you've learned in the first 6 weeks to get it together, because now you're going to be using the inputs on the microbit as well as the outputs. I know the outputs were tricky, but the inputs have a few more tricks. You're going to be getting some code, extra code to work with in the lab packs as some of your starter code for your responses. And the next 3 labs are really going to be directly preparing you to do the second assignment, which will be released next week. So these labs are absolutely crucial for success in that assessment task. Don't let up the pressure. I know that we all have lots of commitments. You've all got lots of courses going on. There's many assessment tasks. Many of your courses are hard. This is definitely a tough course just because the material can be tricky to get your head around. So make sure you're prepared for those labs. Make sure you attend your labs. The most important thing you can do in this course is go to labs. So that's the psych up. After the next 3 weeks, of course, we have some harder labs towards the end, but the labs in weeks 10, 11, and 12 aren't preparing you for an assignment. They're preparing you hopefully preparing you for the final exam. So the next 3 weeks labs are really crucial to your success in that assignment and the final exam, the last 2 big assessment tasks. So these ones are very important to go to. Just as important as the last three labs were, really. Okay. That's enough of my admin corner. Any questions, please ask them on Teams, or please pop a question onto Piazza at any time. Always happy to see a question. Yeah, my small but committed audience has grown by a few people. Great to have you online this morning for our Tuesday morning lecture. So here's the topic for the day, data structures. What even is a data structure? I think that you should have a intuitive sense about this from your previous courses, particularly courses like COMP2300 where you would have talked about arrays. You probably talked about some recursive data structures like a linked list or a stack, the data structure kind of stack, not the memory, primitive memory address kind of stack. You probably think about these things as quite high-level ideas, but what we're going to do today is, as with many topics in COMP2300, take something that you understand intuitively as a high-level idea and break it apart to see how it can be implemented in the lowest level way in assembly programming. And of course, as you might expect, as with all things in assembly, that provides a lot of freedom, a bit of complexity, a bit of kind of scary simplicity when you start to think about the implications of how simple things can be in computers, but also a bit of fun. So we need data structures to I guess, structure data. That's a bit of a impoverished answer, really, isn't it? But a way to keep data in its place and to take care particularly of multiple things at once, whether they're the same thing or different kinds of things, things that relate to other things, things that need to be accessed at certain times in certain ways. But the point of these things is that there's a structure to how we're keeping our data. We're not just throwing things into memory as, for instance, in assembly, as global variables or just labeled memory addresses in our random bunch of stuff in memory. Because if we did that, we would have to have little pointers, keep a little track of every single memory address for every single thing. If we have a structure, we can reduce the number of memory addresses we need to keep track of and instead keep track of important information about our data. This makes our lives a lot easier in terms of writing our programs. We're not having to deal with as many constants. It also lets us play nicely with others. Why is that? Because we can pass data structures around. We might know how big a data structure is and where it starts, and that might be all the information we need, just 2 bits of information that can keep track of a whole lot of pieces of data within that structure. So the first big data structure, and this is the topic for today, we'll do another kind of data structure on Thursday, but arrays is the first important one. And I know people have been playing with arrays already. We've even played with an array in these lectures when we did the capitalizing any string, shouting any string demo in assembly. That was really using an array of bytes, wasn't it? So an array is a collection of homogeneous data, that is data which is the same kind of thing. An array of ints, an array of strings, an array of characters, an array of 2x2 matrices, an array of floats, an array of doubles, an array of bytes. Lots of different kinds of arrays, and you know about them already from working with Java. You might need an array for lots of different things, but a few things you might need, which we've talked about already potentially, is a string of ASCII characters, each ASCII character being a byte. So if you remember the demo, we were shouting any string. We had that string stored as a sequence of bytes in memory with a 0 in the end, and the 0 let us know when we got to the end of that array. You could also have an audio file. So if you had some 8 or 16-bit signed values that represented audio samples, you might have those as a sequence in memory, and you could be sending those chunk by chunk to your audio output using the audio library that we played with in Lab 5. You could have a collection of red, green, blue values, one after another, that represent an image. So all of the pixels in an image could be unfurled out into a big sequence, and that could be an array storing pixel data for an image. And I've certainly seen in this assignment, whoops, where's my pen has turned off, whoops, there it is, somewhere. Come on, pen, here it is. I've certainly seen in the assignments, I want red, people doing things like dot bytes, 0, 1, 0, 1, 0 to represent, this is really an array representing the LED lights in a column or a row, or even the whole microbits screen could be represented there. 25 bytes in a sequence representing each one of the LEDs on the microbit, and then there would be some algorithm within the assignment to make sure whenever it sees a 0 it turns an LED off, and when it sees a 1 it turns an LED on. Good way of dealing with the assignment. I even saw some clever folks who were controlling brightness and, for instance, using a 0, going from 0 up to 255 in a byte for brightness or something. So it might be 127, 73, 130, etc. A bunch of numbers representing brightness, and then they'd have to do a bunch of work to actually display the LEDs at that brightness, which was fun to see. Certainly not required information. Just make sure my drawing goes to the edge of the screen. I like to be able to draw all the way to the edge, and for some reason it doesn't work unless I'm zoomed into 170%. It's because I've got this typical Linux thing. It doesn't work very well with scaled displays. I've got a 4K display, but don't want it to look like don't want it to be completely tiny, so it has some scaling going on there automatically. Okay. you know when you need an array. You've used arrays many times in previous work, and you're probably desperate to be able to use them. So let's have a look at how we actually do that. What's the essential information we need? This is flippant, but an array is just a bunch of things. It's a bunch of things in memory in a sequence. Here are some key information that we need to figure out in order to create an array with an assembly. First question, what are the things? Are they bytes? Are they words, as in 32 bits? Are they themselves an array? Are they, multi-byte, multi-word objects that have, or multi-word data things which have other stuff inside them? Are they just a bit, which is a bit small for an array really? Where are the things? So where do they start? What's their base address? This is related to, I'm going to call this element size. Element size, that's the first thing. What are the things? We need to know how big they are. Now that's really this one too. Those two are related. Where are the things? Where do they start in memory? Base address. How big are the things? That's the same as element size. What kind of a thing is it? How big is it? I guess I'm more concerned in how big they are rather than what they are, because this one is completely essential to making an array. This one, I guess you can make an array of things where you don't know what they are. We don't need to know that information. We definitely need to know how big they are. How many things are there? So that's the length of the array. Now let's just put our thinking hats on here for a minute and just have a thought experiment about this. I want to know how much memory space an array would require. What information do I need for that? I need to have how many things there are and how big the things are, because each thing in the array is the same size. That's my assumption. If I go over here to, I go to my length, I'll call it number. That's going to be how many things there are. And then I've got how big the things they are times element size. That should equal array size. So suppose my element size is 8 bytes. So it's going to be 8. And my number of things is 10. Okay? Then my array size is going to be 80 bytes. Phew, that's not so bad, is it? So thinking a bit further about this, we can start to work out what the address of each of the things in the array would be. I'm probably skipping a slide I'm going to see in a minute, but if we know our base address, if I want to find the address of elements, I'm going to say element address 0, that's going to be the base address, probably, in a very simple array. That's going to be the very first location, same as the base address. If I want to get element address 1, it's going to be base address plus L size, because I'm going to move forward in memory by the size of one of my things, the 0th one, to get to the first one. So element address 1 is going to be base address plus L size. What about element address 2? That's going to be base address plus 2 times L size. Well, this is starting to look good. I can now cut that out. I could say, erase some of my bracket there. Oh well. I could say element address I equals base address plus I times L size. Okay, so now if I wanted to get the 10th thing, which would be element address 9, the 9th index, starting with a 0 indexed array, it's going to be base address plus 9 times L size. And that would get me the very last element in that array at the base address plus 72 bytes. So this information is critical. We can now encode our addressing scheme into assembly and figure out what the address is of any element within our array. We haven't stored these things in memory yet, mind you. We're only talking about the addresses of these things in memory. We'll talk about storing them in memory in a minute. So, just a high-level question here. Can you fit an array into a register? A register has how many bytes? 4. Let's just say R1. That's going to equal a bunch of words, 4 words, OXFF, 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 OXFF. So really, I guess if you had a 4-byte array or a 2 half-word array or a 1-word array, which I guess wouldn't be an array if it's only got one element, that could go into a register, but it's not going to be very useful. So arrays are something which are really completely linked with memory. And I think today is the day. This is the part of the course where really memory is the more important thing than registers. Registers were great. We loved living in a register land from weeks 1 to about 4, maybe 5 if you were lucky. But now you can't live in a register land anymore. So registers are something you're going to be using all the time, but they're not your most important place to store stuff. Your most important place to store stuff is memory. You need to be using memory a lot. If you haven't used memory yet, today's the day to start. Because a register can't fit an array. A register can't fit any significant amount of data. Registers might get changed at random times, which we will find out about next week. And registers are just, you know, kind of a temporary, small, ephemeral thing. You need to be using them all the time as your working tools for doing calculations, but you're not storing stuff there permanently. And if you are, really, it's not how you're supposed to do it. So trying to fit an array in a register is a lot like trying to make a coffee inside a small saucer, or I don't even know what is being held in this person's hand here. Nothing like, there's nothing like something that's going to work. Absolutely not going to work. They're just holding a portafilter? I don't know. Probably not. You can't fit arrays into registers. We need to store it in memory. Here's an example of an array. Now I've got a lot of images in this talk with quite low contrast. I think you can see them. I hope you can see them. They certainly look nice on a grey background, and it's not going to burn your eyes out if you're watching this at night, which you probably are. So here's an array starting at our old favorite memory address, OX200000. This is the first accessible, first memory address for storing stuff and for data storage. So it's right at the base of memory. And this array it's very convenient. This array is full of element size 4 bytes or 1 word, 4 bytes. That's the same over here. Each thing in this array is 4 bytes. So the first one starts at 2, next one is 2, 4, next one is 2, 8, and then 2, C. I hope you can count in 4s in hex. 2, 16, 2, 20, 2, 24, 2, 28, etc. So you can see this nice pattern of counting up in 4s in hex. It's always 048C, 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 because it's 0, 4, 8, 12, 16 is counting up in 10s. It's like counting in 5s in base 10, which is always easy. It seems like when I was a kid we had to count in numbers in primary school, and counting in 5s was somehow satisfying because it's so easy. I'm not sure why I'm telling you this. Okay, now we've got over here our indexes. So we've got here memory addresses, and over here indexes. So these indexes are the count, or the count that points to each member of the array. And this is a pretty simple thing. It's just a stack of things, or not, I'm not going to use the word stack, it's a pile of stuff in memory. And all of the things that are in the pile happen to be the same size. And that lets us access them pretty easily. Is that an sufficiently abstract description for you? So addressing, we've talked about indexes. What are these indexes? Well, when you're using Java and creating an array, you might have an array called the things. That's the array name. And then the index would be a number within the square brackets. And so you could access things from the array by using indexes. What does index mean? It's a word coming from Latin which means something that you're pointing to something. So an index in a book points to where certain words are found in that book on a page number, and an index in an array are numbers that point to a certain element of the array. So back over on this page, you could see index 1 is pointing to that location, index 2 is pointing to this memory location, index 3 pointing there, index 4 pointing here, pointing to the start of each of these array elements. That's an array element, that's an array element, that's an array element. This is art attack, yeah. And this one would be, the base address is kind of pointing to this, or the name of the array in some sense. This is not exactly how it works in Java, but it's close enough for, I'm not going to say I know how it works, it's just, I'm simplifying things to correlate between high level and low level. The name of the array is sort of correlated with the base address in memory. Okay, how do we do it in assembly code? Well, it's all just loads and stores. You've been doing this all along. You know how to do it. Here is an array of things, the things. It's got a label. The label means that it points to its base address in memory. .word 23006300. 2300, 6300, ha 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 ha. And then we've got a .text section. So that's a .data section, and the .text section is code. This is data. .text is code. And we've got some kind of label just pointing to some code. It's not a function at this point. Letter R0 equals the things. That's going to get the base address of this sequence of words stored in memory. We can load up the first element just by loading into R1 whatever is found at the first memory address. That's the things, remember this one from before, plus 0 times element size, which is 4. And then we can get the fifth element by saying the things R0, comma 16, 16 being 4 times 4. The thing plus 4 times 4. It's the fifth element because we always start with index 0, right? So the first element is index 0. I guess I would call it the 0th element. And then the fifth element is index 5. Sometimes people say the 0th thing in a list just to emphasize that we're in 0 addressing. The fifth element. I think this is a joke. My friend Ben Swift made these slides some years ago, and I've been editing them ever since. And the fifth element is a famous sci-fi movie directed by a director called Luc Besson. It's a very stylish movie, and now looking back on it, incredibly sexist. So I don't know. Watch it for the style, but then just like keep your critical thinking hat on. Alignment. Oh yeah, alignment. We haven't talked about this yet. I'm going to copy this code. No, I'm not. I'm not going to draw on the screen. I'm going to copy this code into VS Code, and we're going to play with it, but in a minute, because I want to talk about a few more things first. So I'm just going to pop this stuff here. I don't know what I'm going to do. there. We'll just have the things hanging out there. I think I might have another array somewhere in a minute, but I want to make sure I'm not missing anything when I come to do some demos in a sec. Alignment. Now, we had this interesting situation where in the first example, this is what we've already seen before, all of these elements are on a word boundary in memory. So if the first bit of memory is 0, next one's 4, 8, C, 10, 14, 1, 4, 1, 8, 1, C. All of these are divisible by 4, 0, 4, 8, 12, 16, 20, 24, 28. So if address mod 4 equals 0, then we call it word aligned. So, you know, the kind of, we have bytes as the minimum addressable thing in memory, but also words, 32-bit words, are very important in our Cortex-M4 CPUs on our microbits. So the fact that we have these 4-byte words is kind of a part of the design that permeates a lot of different things in these boards. Even though we often use bits of data which are smaller than a word or bigger than a word. A typical smaller thing is a half word or a byte, and bigger things would be a double word, 64 bits, 128 bits, 4 times the word. So it's important architecturally because a lot of things in the way a CPU is set up are organized so that words are prioritized and other things are not. So even though we can address memory with a byte, it's often important for things to be aligned to words. I'll tell you why in a minute. Just to show you the opposite, or a different way of doing it, we've got these bits of memory where the very first byte is empty, nothing in this one, nothing in here, and then the first entry starts there. So they're all offset by 1 byte. So if any of these addresses was modded by 4, add mod 4, they would always give me 1 because they're offset by 1 byte. So these are unaligned data. Aligned data is always on a word boundary. That means its address is divisible by 4. Unaligned data is not on a word boundary for whatever reason, right? It could be data which is 3 bytes long, so it's all squished together and you just end up with data which is starting at either byte 0, 1, 2, 3, 4 of any word. So the question here is, what's the big deal? Why is unaligned something I'm even talking about? Are these even a problem? What's the big deal? The good news is that if you say letter, just start again. If you say letter 0, R1, comma 1, so presuming that is OX 20000000, and that's making it an unaligned load. You're loading 1 byte past the word boundary. This will work fine. You will get the data you expect. What you may not know is that it takes twice as long. Because actually what has to happen here is that the load internally inside the Cortex-M4, whenever it's loading from memory, it can only ever load on a word boundary. So if you ask it to load unaligned data, which is not on a word boundary, it says, fine, but it loads the first word, it loads the second word, and it smushes the bits together and cuts off some to give you what you want. So that's, it does this internally, but you don't even know about it. It's a feature of the CPU that it lets you do unaligned loads and stores, but it sort of, under the covers, takes a little bit longer to do it. So there's no problem at all doing this. It's just going to take you a little bit longer, or it's going to take the CPU a little bit longer. If I go to this website, if we check out the load store timings, which is a whole section on this website, this section describes how to best pair instructions to achieve more reductions in timing. So this is it's something that could help people to optimize their code to create the fastest code possible on a Cortex-M4 processor. Here we go. Unaligned word or half-word loads or stores add penalty cycles. It's not a penalty in which, like, no, very naughty, we're going to take away a cycle from you. It's a penalty because it has to do more than one load to do it. A byte-aligned half-word load or store adds 1 extra cycle. A half-word aligned word load or store adds 1 extra cycle. A byte-aligned word load or store adds 2 extra cycles. So it's actually going to take 3 cycles when it probably should have taken 1 originally. It has to perform the operation as a byte load, a half-word load, and then another byte. So it's going to do, you can imagine this in memory as, starting in the bottom. I'm going to make this really big. These are bytes. 1, 2, 3, that's 0. 1, 2, 3. 0x2, 0, and there's the last digit. Next byte, 1, 2, 3, I'll just keep counting, 4, 5, 6, 7. So what we've said to the processor is that we'd like it to load these bytes, please. And what it actually does is load this byte, this half word, and then this byte. So it's having to do 1, 2, 3 loads. Sorry, that's just how it has to happen that way. That's the way that the CPU is designed. So if you're doing an unaligned load, it's slow. You can imagine if you had code which you were trying to optimize, which had to load 1,000,000 things from an array, then if you had all of the elements in your array as word aligned, that would take 1,000,000 cycles. If you made it not word aligned, it would take 3,000,000 cycles. So you're adding 2,000,000 cycles, twice the amount it would have taken just to get it to, just because you've got unaligned data. So if you were designing a program, you might think to yourself, I can actually optimize the speed of my program by making sure that my data is aligned. And I'll show you in a slide in a second, there's a way of dealing with that situation. So you can put anything in an array, not just words. Words are 4-byte chunks. You can, of course, put half words, bytes. That was our array of letters, was an array of bytes. You can put double words. You can put long things in arrays. It doesn't matter how long they are. The element size can be any number, more than 0, I suppose. But the concept of how an array works in memory is the same. Here's some double word sized array elements. So the first one is taking up 2 words in data. Second one, 2 words in data, 2 words in data, 2 words in data. If you had to get those array elements, you'd have to do 2 loads for each one. No big deal. This happens all the time as well. Load first one. If you want the first element of the array, or the 0th element, you'd load the first half, then the second half. Or it might be that, like, there's just bits of this that are important and you just want that byte. So you might take the base address and then just do a single byte load just to get this little bit that you're interested in for some reason. I don't know, I'm making that up, but you'll see more about data structures where you'd want to just take bits of them at a time on Thursday. Here's the concept, or a potential solution for unaligned data in your .data section. Here's an array which is what one might call packed. So this array has 3-byte elements, and they've all been packed in, which is unfortunate because that means that they're not on word boundaries. And if we had 1,000,000 of these things in a big array, and you had to iterate over that array all the time, that's going to cost you a lot of extra time, a lot of extra cycles. So a solution is that you just add some space, padded. Just add a byte that's empty. You know, we got a lot of memory. We can waste memory. We can't waste cycles. It's another one of these moments in time where we sometimes have a trade-off between time complexity and space complexity in computing. You can make your program run faster if you make it use more memory, because it's allowed to pad out arrays and thus speed up array accesses and stores. So here's a thing just to reiterate right at this point. In Comp 1110 and Comp 1100, and any other computing course that's not 2300 really, when we talk about data types, data structures, we often talk about what they mean is the abstract constructs of a high-level programming language. When we're talking about data structure in Comp 2300, we mean how the bytes fit in memory and how you're going to get to them using assembly. So this is, you know, high-level things that make sense to a programmer. High-level makes sense for humans. And this is bytes in memory. You know, it's challenging how simple things can be in Comp 2300 sometimes, isn't it? The raw simplicity, but the scale of it can be challenging. Like, you know that there's memory, which seems okay. This is quite simple. There's just bytes and we have to access them. But there are so many of them. Which byte do we need? Right? The scale of this is difficult. We have so few handholds to help us to understand it. That's why people invented abstract data types and high-level programming languages, so that there'd be more kind of cognitive handholds to help you understand and work with data more easily. When we're doing data structures in 2300, there's nothing to grab onto. Nothing to grab onto. What do I mean by that? There's less sort of syntax that helps you understand which element of an array you've got. You have to do all the calculations yourself. Working with arrays. Okay, finally we get to do some coding. They don't fit in registers, so we have to operate on these things one element at a time. Iterate through the arrays, get an element in, do something with it, and move on. We need loops, and that's what we did. The very first loop, if you remember back to, I think it was in week 4, when we were looking at loops, I gave you a loop example iterating through a sequence of bytes in memory. That was an array. So here's a kind of bit of code, I guess could be C-like, which is going to be, we're going to turn into assembly code in a matter of minutes. Given an array of word-sized integers, find the sum of the elements from the from index to the to index. So those are, our array is a part of this a parameter of this function. The from index is going to be a parameter and the to index is going to be a parameter. And we know that these integers are word sized, so 4 bytes. So we'll have some variable here, a local variable to be the sum, int acc, we'll call it accumulator, equals 0, and then a for loop, for int I equals from index, semicolon, I less than or equal to to index, semicolon, I plus plus. And then, so we're going to access each index of the array, starting with the from index, up to the to index, and add whatever we find there to the accumulator variable, and then return that as the output of our function. Can we do this in assembly? Yes, we can. Here's our array. Oh, I'm going to copy this bit into my VS Code. I knew I'd need something at some point. is called array. Not a very expressive word for it, is it? Okay, just so we're aware, the sum of all of these numbers is 14, or OXE. I'll put that in VS Code as well. Now, I might just move over to VS Code permanently in a minute, but I'll go through, maybe I'll go through the slides a bit and we'll just try it out when we get there. So we'll need a few things. We're going to need our base address of the array to be in a register. We're going to need our from index and our to index. So our from index is going to start at 0. This is the indexes 0, 1, 2, 3, 4, 5, 6, 7. That's a very bad 6 and a bad 7. 0 indexed array, the last index is 7, so we're going to be adding up the entire array. Copy this data into your VS Code now. I really want to have a function to do this. And I forgot how to do that function. I thought I had the function snippet organized here, but I don't think I do. Dot type array sum function. Oh, I do. Cool. I forgot how to use snippets. I'm not a snippet person often, which I know is possible you think badly of me because of that. But realistically, sometimes people are snippet people. They want to have all their snippets organized in their editor of choice. Sometimes they're not. I think I'm just in the latter category. Array sum? No. It's the wrong kind of sum. What am I on about? I am a person who likes to spell things correctly. I should have just started again. Okay. We've got my array sum function. So these are our parameters of our function. And then we're going to BL into array sum. And we expect our answer to be in R0. R0 after that. Cool. So, how do we start in our array? We look at the base address, and we start looking at the indexes and creating the address for each element that we want to take out. So, if our from index is further up in the array, we need to start at this item, create its address, load that item out, then this one, then this one, then this one, and then stop. So we need to use those from and to indexes to help bound our loop. How are we going to do that? Here's a first idea of how to do it. We make a register as our accumulator. We create a bit of data which is going to be our element size, and then we're going to do a loop to do that array. The loop here is called array sum, which is slightly annoying. And then in each element of the loop, we calculate our offset, load with offset, update our accumulator, add R3, R6. This is the actual bit of work. Increment our index, and then choose whether we're going to keep looping based on R2, which is the to index. So you can see that this number here, R1, that was the from index. We're actually incrementing that each time. So we're changing it each time as part of our program. So let's have a little go at how this might work in code. I've forgotten how it works already, so, I don't know. Mov R3, 0, that's going to be our accumulator. Hope you can see this code. Mov R4, 4 bytes. That's going to be our element size. And now I'm going to do the array sum loop. Within my array sum loop, I'm going to start by calculating the address element to load. So perhaps I'll do mul r5 r4 and what was it, the from index r1. Offsets. And so the offset of address of each element to load is going to be index times element size. So that's the element size, R4. I'll do it in the right way. Index is R1 and element size is R4. Base address in R1, element size, no, it's not there. What is it? From, that's base address in R0, from index in R1, and to index in R2. Okay, now I need to load in my data. Now I've got my offset and I've got my base address, so I can use an offset load. Pretty handy. Just use another register here. Just keep using registers until we run out. Shouldn't run out in this instance. And my base address is R0 and my offset is R5. Okay, and now I'm going to, this is load array R1. I'm going to add that to my accumulator, add R3, R6, add to accumulator. I'm going to increment my from index, add R1, 1. And then I'm going to check if I should go back to the start of the loop again by doing a compare my from index with my to index. So when the from index is sort of coming up and when it gets to the to index, that's the last time. If it's above the to index, we want to not do any more. So the last time is when they're equal, so that means I need to do BLE array sum loop. If we don't branch, we just drop through the loop and we need to return our value. So we're going to mov R0, R3. This is put the return value in R0. Okay? Everything good? I'm not seeing, no one's complained yet. No one's complained this whole lecture about anything I've said, which suggests to me that everything I've told you this lecture is 100% unalloyed truth. And because normally if I say something wrong, people jump down my throat on the streams. But my small but committed audience haven't complained about anything. So if you've got a complaint, please register it on the team. Shall we try and see how this works? Boy, I hope it compiles. Got a microbit plugged in, don't I? Yep. Any breakpoints? Okay, get my array address in loaded up. 0 is my array address, which is 2 with a bunch of zeros. 1 is the to address. 2 is the to index. We're going to, now we're in our function, so I'm going to put a 0 in R3, that's the accumulator, and the element size of 4 in R4. And now I can go into my loop for accessing the array. First thing is calculate the offset address of the first element, which is going to be 0 times 4. So it should be 0 in R5, no big deal there. I load my value in from memory, which should be a 2, a 0. I can't remember what it was. What is it? It's a 2. That's good. 2300, 6300 was the array of those digits. Then I'm going to add 1 to my from index. R1's now 1. Compare those, and I should be able to go right back to the start of my loop, and it does. Calculate the offset, which should now be 4. It is there. R5 is 4. Load in 3. That works. And then we add that to our accumulator, which is now 5. Correct. Add the 1 is 2. Go back to the start. Okay, I'm just going to skip through this for a while now. Has to load in 2 zeros, which is fairly boring. But my R5, you can see, is going up by word values each time. It's up to C. The next one is 1 0. The next one is 1 4. Then 1 8. Then 1 C. I've forgotten how many more we do. That's it. Put our return value into R0, OXE, which is also 14, 2 plus 3 plus 6 plus 3, plus 4 zeros. And we return, and we've got our answer of our array sum. Now, before we go today, I've got a few more things to talk about, which are, is there any possible way of making this faster? Loops are one of the things that can really slow down your program. And we've already talked about one way which it could be slowed down, which is in an instance of having to do unaligned loads, which can really slow down your code. But there are other ways that other things that can slow down your code. And basically, basically what I mean is that there's a bunch of stuff here in between this loop. At the moment, we're only looping over 8 elements. So if you've got a couple of instructions, it's like 8 times that number of cycles. Each of these instructions is basically a 1 cycle operation. 1, 2, 3, 4, 5, all 1 cycle. So 5 times 8, 40 cycles. Like, that's nothing. The microbit is running at 64 megahertz, 64 million cycles per second. So 8 cycles is nothing, or 40 cycles is nothing. But if we were going over 1 million elements in an array, 1 million elements, 1 million cycles is a 64th of a second. Well, that's still pretty quick. Too quick really for us to almost detect if it was slowing down your code somehow. But if you had 8 times 1 million, that's definitely detectable. If that was slowing down your LED turning on or something, you'd definitely know about it. If it was slowing down by a, what are we talking now? 8 million, that's, by 8, sorry, excuse me, that's an eighth of a second. You'd definitely see that if it was slowing down your LEDs, and it would be frustrating and annoying. So is there some way of reducing the number of cycles to get your code to run faster within these loops? Because the loop bit has to run for every single element of an array if you're iterating over the whole array. Well, folks, I'm here to tell you that there are some cool ways that we could be iterating over the array. How did I get 8? Oh yeah. So we've got 2 instructions in the setup here and 6 in the loop. And the 6 instructions in the loop are really the ones which are going to cause issues if you're iterating over a long array. Here's another idea. What have we done here? Instead of using the offset as a number and doing the mul, we're going to build the multiplication or the calculation of the offset address inside the load. So you can do loads with a built-in logical shift left. That's really handy because you can use it as a multiplication. So this instruction is going to load what you get at R0 plus R1 shifted left by 2 places. What does R1 shifted left by 2 places mean? R1 times 4. exactly what we wanted it to do. So we're doing the whole thing in one single instruction, one cycle. You know how clever these ARM CPUs are. They can let you combine a shift inside lots of instructions. Just going to the cheat sheet for a second. You can see this really clever operation is defined here. The indexed offset indexed load with a shift. Really, really cool. I think maybe you can only do LSL there. They really set this up for this exact purpose, right? Speeding up accesses of offset data in an array kind of data structure. Then everything else is the same. So we've saved the mul. Now we've got 5 in loop, 1 instruction in the setup. I'm not too worried about the setup. Like, that only happens once, right? We're worried about the thing that we run 1,000,000 times, not the thing that we run once. So the problem here is that the size of thing must be a power of 2. Often the sizes of things are a word, or they're 2 words, or they're 4 words. So maybe it often is a power of 2, but it has to be for this to work. Oh no, my coffee's gotten very cold. Maybe it's colder in this room than I thought. That's a chilly coffee. This is number 2, attempt 2. Here's another optimization. I don't know why my font goes weird when I change slides. Something odd in Firefox today. We're not really saving anything in the loop here because we're adding an instruction in the setup, still 5 in the loop. The idea here is to, rather than have an index, we're going to have a starting memory address. And rather than have a starting offset memory address, and rather than having an ending point, we'll have a finishing offset memory address. So these are going to be multiplied by, or shifted by 2, multiplied by 4, in order to get us a memory address in terms of element sizes, or an offset in terms of element sizes, rather than an index. And that means you can skip the mul as well. So we've also skipped the mul, and we're using R1 as an offset instead. So this will start at 0 if it happened to be 0, and that one was 7, so it's going to be 7 times 4, it's going to be 28. Or what is that in hex? 1C, I think. Tell me if I'm wrong. Yeah, 1C. OX1C. So this again saves us 1 in the loop, using byte offset instead of element index. You know, the good thing about this one is we can use this we still have to increment the index here. We can use this one to do the optimization we did before, except for things that are of any size, not just powers of 2 sizes. So I really liked the previous optimization. It's really fun and cool to use LSL inside the load instruction. Doesn't it make you feel like you're like galaxy brain mode on microbit programming when you do that kind of stuff? But this one works for a more variety of arrays. Okay, I think there's another idea about how to speed this up. I've got 2 more slides, I think. Ooh, this one's getting pretty wacky now. So we got 5 instructions in the setup, putting a bit more setup in there, but only 4 in the loop. How do we do this? Well, the cool one here is that you might have thought maybe this line here, the increment line, maybe that one can be optimized out somehow. And the way to optimize that out, if we go to the cheat sheet, would be to use these post-offset load and store instructions, just the load instruction. So the post-offset one, if there's a comma after the square brackets, that adds a constant to our address register after doing the load. So if we if all we did, oh, where's my slides? If all we did was add a comma here, yeah, comma, and then a constant, 4, we don't need to have the pound sign, but I put it there anyway. If we have that comma, that will actually we can just remove this line straight on, I think. We don't need that increment index. Well, that was cool. So why don't they have all that extra setup? Change index to offset. Because we're not using the offset, we're changing to, excuse me, we have to do a few extra things. We have to change so we don't need our base address anymore. So we're not doing an offset load and store, we're doing a regular load from a single address and then post-indexing by 4. So this R1 has to be turned from an index to an offset, and then we add it to the base address. So it's now R1 equals base address plus from index times 4 in brackets. So we're, rather than indexing through our array with offsets and waiting for the offset to be the right number, we're just indexing with raw memory addresses. Totally fine, we can store any memory address we need inside one register. Registers are 32 bits, memory addresses are 32 bits. No problem doing this at all. Then we're allowed to, or we're able to do this post-index thing and save those extra instructions, save one extra instruction. That could mean a significant difference in the speed of an array running. If you're doing it all through your code, this could make a big difference. Yeah, so final points on optimization. Loops are often the hot part of a program. They're the bit that runs over and over again, and if you optimize something inside the loop body, that can make a big difference to the actual speed of your code. Optimizing compilers, as we saw in last week's lecture, in week 6, the compilers can do some weird stuff to get the most optimized code. When you turn on all the optimizations in a compiler, they're just rewriting your code to make it work better. That's what compilers are good for. Hooray for compilers, but in 2300, of course, you have to be the compiler. So in general, a good general idea is not to optimize too much straight up. Make sure your code is working and it's simple, and if you find you want to speed things up, get your hands dirty with optimization. Start doing some crazy stuff like you've seen us try just then. It's not the craziest stuff in the universe so far. The more I teach this course, the more reasonable it seems. So all you have to do is teach 2300 for 3 or 4 years, and then you'll start to feel like these things make a lot of sense. Lol. A few things to remember about. Don't forget about endianness when you're loading from memory, loading arrays. When you load a whole word, it's turning the half words around from some perspectives. Remember, load lit and store, just load words, not elements. So if your elements are word size, use lit. If they're half word size, you should be using lit H, really. And if they're byte sized, you should be using lit B, byte sized snacks. So watch out if they're bigger than that, you might have to do something else. And so far, we haven't got any bounds checking. So if you were doing, if we asked our array sum function to go up to 10, it will do it, even though there's only 8 elements in the array. It's going to start reading data after that. And we don't know what it is. So there's nothing stopping our program from reading data after the end of the array. Normally, if you tried to do that in Java, it would say array out of bounds exception or something, right? But in assembly, there's nothing stopping you from doing it. So you have to make sure you build your own guardrails in, or you're careful about how big these arrays are. And we weren't that careful about the procedure call standard. So if you're writing this kind of stuff in your own code, make sure you're saving the variables that need, the registers that need to be saved, etc. What are we talking about? Oh, more stuff. Really? Okay, a few more slides. A few more minutes and then we'll be done. Memory allocation for arrays. There are two real options for memory allocation in arrays. The static option is that what we're doing right now. We're putting our whole array into memory at compile time. It's all there in our .data section. That means that the allocation is already done when the program starts, but we need to know the size of the array in advance. We could actually make a big array. Suppose we wanted to have an array that we then fill up with data. We could do something like this. Just have it as zeros. I think there's some way to do this quickly, right, with assembly directives. Right, you can have lots of elements here. There's some way to just get it to set aside like 20 bytes, fill it full of zeros. Someone in the chat will tell me, or they won't. I'll probably remember how to do it by the start of next week's lecture. So you can set aside a whole array that's empty space in our .data section. And if we know how big it is, we know how much space we need, that can be really convenient. This is what people were doing in assignment 1 really, right? Because you were, someone's saying there's some repeat command. Yeah, but what is it, Joshua? Yeah, but what is it? I can't remember. This is what people were doing in assignment 1 because typically they'd sorted out a whole show if they wanted to store it in memory, and putting a lot of data in their .data section is basically allocating all that memory at compile time before their program runs. The other option, and we're going to talk about memory allocation next on Thursday actually in more detail, which is going to take some time, which is why I want to get through this little slide of prep right now. The dynamic option is when, while you're running your program, memory is made available. So you might run some function which finds the first bit of memory that isn't used for anything, and then you say, I want to have 128 bytes stored ready for my array, and you make some space. So you might use the stack if you're inside a function, which you always are in your program. The main label is a function. You could use the stack and say, this address is the start of my array. That's what SP is right now. Change SP to be SP minus 128 and give yourself 128 bytes of space to store an array. Or you could do that in the .data section if you know where you're up to in that data. The pro of this is that you can pick the best size when your program is running. Suppose you don't know how much space you need in your array because you're waiting for input from a user or something. That means you can dynamically allocate an array to the size you want, but you have to do this while your program is running. It takes some time, and if you want to resize it later, that can be a little bit tricky. There's a whole, we'll return to this later because there's a whole complex field called memory allocation, which is something that compilers and operating systems kind of work together to use memory effectively and efficiently. We're not going to go into great detail in this course, but hopefully we'll touch on it enough so that you start to see what the problems are and how hardware and software has to work together to solve them. Our array so far is very bare bones. It doesn't really work well, particularly because it's easy to fall off the end and end up reading some other data that wasn't part of it. It's just the raw data. A few improvements we could make. We could have a 0 at the end for terminating, just like our strings, or some special thing at the end which terminates it. There are ways of storing the array size along with the data. And we could think about how to make a resizable array after thinking about that. So one way you can deal with arrays with size, you can store their size as the very first element. Very good way to do it. Then your first or the 0th index is the base address of the array plus 4 in this case. So we've sacrificed one element of the array just to store the size of the array. Very good idea. And it makes making sure you're not running out of bounds much easier because every time you access from an array, You could just say, oh, is the number I'm trying to access more than the array size? If it is, don't do that. Do something else, or assume that you've finished your work. If we wanted to have a resizable array, one of the issues is that we really need to allocate memory at our starting point. So we might just say, okay, we think the user has asked for a resizable array that is going to take 3 elements. I'm just going to give them double that just in case. So we might allocate 7 or 6 or 8 or something, some larger amount, and give them an array which is going to contain their current amount of data and hope that we can contain more data than that when the time comes. So this particular array, the first element, this array design for a data structure, if I say design a data structure, this is the kind of stuff I want to know. This array design includes 1 word to store the allocated size and 1 word to store the current size of the array. So of course, if we're trying to access something in index number 3, this array shouldn't let us, or it should know that that's unused data so far. We don't know what's there. We haven't written to it. We can't assume it's a 0. We just don't know what's in there and know that we haven't used it yet. If we try to allocate or try to use more addresses, it should be fine storing into addresses 3, 4, 5, 6. But if we tried to store into index 7 above the top, the array, whatever we're using to address this array, should stop us and not do that, because we know that after index 6, it's not our array anymore. It might be someone else's data. If it's on the stack, it's very likely to be data from another function or some other local variable which you've stored. And we get back to our slide. This is the last slide for the day. Our slide of all these 1s and 0s. And the point of this slide is to say, when you're dealing with arrays, we need to remember those questions that I asked. Where are the things? How many things are there? How big are the things? The 3 really core questions, because your memory is just this big mass of 1s and 0s. There's nothing particular about your memory which tells you where arrays are. So if you want to find an array, you better have a label that points to it. This is my array, array 1. And you better make sure that you know how big your array is going to get and what the element size is, because otherwise you don't have any way of actually distinguishing array data from the huge mass of 1s and 0s in your memory. So this concludes our lecture on arrays. On Thursday, I'm going to talk about a second kind of data structure for COMP2300, records. And we'll talk a bit more about memory allocation then as well. You will need arrays in this week's lab. You're going to be using them. You'll be using data structures in general. It's an exciting and fun lab working with creating some Morse code blinks on your microbit. It's a good lab because it reinforces everything you've done in your assignment and pushes you a little bit further in loops and functions and data structures. So I hope you enjoy the labs this week. At this point, I've only had one comment from one person in the whole lecture, but at this point I'm going to say goodbye for now. I will see you folks on Thursday morning. Good luck with your study for the mid-semester exam and all of your other assessment tasks, which you no doubt have for your other subjects. If you're listening on Tuesday and you're in Canberra, there is a study event organised by the Computer Science Students Association on ANU campus this evening. A really great opportunity to go and have some fun playing with the assignment questions and chat to some tutors about stuff. So I will see you folks on Thursday morning. Until then, catch you later.